morning, guys. So if you haven't done so, you can put your homework 5 right here. And today we will continue the discussion from last time about cost analysis model. Okay. And last time we were at the clustered index files, and we haven't finished it, so I'll continue it from here today. And before we start, I'll just quickly put down the variables we'll be using. You recall B means the number of data pages. R means the number of records per page. And D is the I/O. Okay? So let's continue the discussion on cluster index. So yeah, I'm sorry I forgot about homework 5 that the table actually include also cluster index and uncluster. So if you guys got the email yesterday, you don't have to fill that out for those rows. Okay? Let's take a look at cluster index file. Where did we finish last time? I think equality search? I forgot, but then I put the answer all the way to range search. Okay, if you remember, let's quickly review about cluster index. Last time we talked about, here we said empirical study shows that the pages usually have 67% occupancy. So we say actually the 67% comes from what fraction? 2 to 3. So in 2 to 3 equals to 1 over 1.5. So if we in total have B data pages, then physically we actually have how many pages? It's on the slides. $1.5B, right? The reason being, we are talking about the occupancy right here. So occupancy are saying, okay, out of all of the total physical data pages we have, how many pages we actually have data stored in there? So right here we say we have B data pages, we have data in there. So it means if the occupancy is 67%, then we only have, we in total actually have 1.5B data pages. Okay? All right. And if you recall, starting from last time, at the very beginning, we talked about heap files, right? And the simplest analysis is the scanning for heap file. And we say if you want to scan all of the data pages in all of the, if you want to scan through all of the data pages, then the cost is the number of data pages you have and 1 I/O per page. Okay? So for the heap file, the cost rate will be B times D. Correct? So how about cluster file? If in total we have 1.5B pages, then what should be the cost for scanning all of the data pages in cluster index file? 1.5B times D, right? Because for accessing every page, you would need an I/O cost, and the I/O cost is D. All right? So you're just basically saying I want to times the number of data pages that we actually have with the cost for an I/O. Okay? And last time, a little bit more complicated is starting from the search. Right? So starting from cluster, that's where we will talk about the tree structure. So if you recall last time, we talked about tree structure like this. We have indexes organized in this kind of hierarchical way. And if in total we have 1.5B pages, okay, you can think of every node as a page. Okay, if in total we have 1.5B, and for one node it has F children, okay, here numbers F, What is the height of such a tree? Log f as the base and 1.5b, right? And that was the quiz for last time as well. And why do we want the height of the tree? What are we trying to look for? Okay, so the reason we're looking for the height is because if you recall the structure for indexing, right here, everything organized in hierarchical way are the indexes. And you go all the way down, your goal is to reach the bottom to find the data entry you want, right? So it doesn't matter what, you will always starting from the top and reach to the bottom of the tree. So top we say it's the root, and to the tree, how many steps will we take? And that number of steps is the height of the tree. Okay, that's why we want to look for the height of the tree, right? So here the reason we found the height is because it doesn't matter what, the search always have to go through this many steps. And whenever we go to one step, it means we are retrieving one data page. And one data page costs us, reading it costs us 1 IO. So that's why you will see right here, for searching, I put equality select. The match only one record, the cost of it is d times log base of f 1.5b, right? Because that's the number of steps we will take times the cost for each step. Is that clear? Okay. So that's for searching. And here I also have if we are not matching just one result, but more than one, then the cost of it is just very simply the cost for matching one and read the rest sequentially. Okay, here we can say we just simply plus read the rest sequentially is because for cluster index, if you recall, at the end said this is a data entry, right? And here are the actual data records that we want the entry to locate. Then for data entry, the way it's gonna pointing to it is all gonna be kind of clustered based on the order of the record, right? So they won't cross each other, these pointers, okay? So later on you'll see in uncluster it's not that way. If you recall in the previous lectures we talked about in uncluster structure, then maybe it's potentially this pointer can point all the way to the end of the data record. Okay, it's not in this way. It's more like a cluster order. Okay. So here you also see for range select, the cost is the same. Okay, cost is the same for when we match more than one record for equality search. How about insertion? What do you think will be the cost for insertion? So if you recall last time, the very basic structure is the heap file. So we don't really care about where we actually input the new data record. So we say the assumption is we just always append it at the very end of the data record, right? We just append it at the end. So there's no cost of searching the right position to insert. However, when we talk about sorted file, then where you insert the new data actually matters. So you want to find the right position first, put it in, and rewrite the rest, right? Because if it's in sorted file, you can think of it as one-dimensional, and everything is sorted in some order. And today, if you want to insert new data, say it's supposed to belong to this position, not only do you have to spend the cost finding the right position first, after you insert it, you have to rewrite all of the rest again, right? Because now it's taken the place, so they all have to be rewritten again. So that's for sorted. How about for cluster? So in this one, this is the cluster structure. You can imagine the steps as so. You first, again, you have to search for till the right page in the leaf, and then you just simply do the right. That's all. Okay? So what's the cost for searching it? Then that's what we saw earlier. the number of steps times the cost for each step, right? And how about writing? Writing is NIO. Okay? If you recall from last time when we talked about the very basic insertion for heap file, we say the cost for insertion is 2D. So where does each D comes from? The first one you can think of it the same as writing it. Okay? This one is actually reading it. Or you can do it the other way around. For inserting into the heap file, so it doesn't matter what we just append at the end, we have to first read the last page and then write all the records. So each of them takes 1 IO cost. Now you might wonder, okay, so that takes 2D. Why do we only add 1D right here? Because the D for reading was already included in the steps, right? Because for each step, when we are traversing to the tree, in the tree, we already read through the pages, right? Got that? So this is the cost for insertion. How about deletion? Any thoughts? Deletion, again, you can think of it as just rewriting the corresponding data page again, but it's just 1 record missing. Yeah? You got the answer for deletion? No. Deletion, so again, for deleting, you are deleting a record, right? So you're deleting a record from a page, and that's essentially the same for rewriting that page, but just with 1 record missing. So that cost itself, again, is D. And what do you want to delete? That's still based on, you need to search for it. Correct? So, deletion, the cost of it, is the same as insertion. Okay? This is the insertion, that's deletion. So let's go cluster. Let's take a look at cluster. For cluster, if we want to reuse this graph again, the same thing that it shares with cluster index is the structure of hierarchy. But down here is different in a sense that now the pointers are not allocated in a more cluster manner. So maybe this first pointer in this data entry page. Okay, so again, if you forget, there's a data entry, and below is data record, right? Record is where the actual data lies in. Okay, so for data entry, the pointer, maybe for this one, it can go all the way there, right? And maybe the second one can go here, and maybe here, we can go here, okay? Just to give you a sense that it doesn't have to be in a cluster way. So how does this affect the cost for each operation? So you can see right here, the first thing I wrote down there is assume that the size of data entry in the index is 1/10 of data records. Then if the data pages have 67% of occupancy, the number of leaf pages will be about 0.15B, right? So you can think of here the number here. The number of lead pages will be about that. Then the number of data entries on the page is around 6.7 R. So here is the first time we talk about R. So the whole point right here, I actually don't really want to touch on R. So R is the number of records per page that we didn't really use that much. So initially I planned to go in detail of the scanning cost. I kind of regret it, so we will just compare other ones. But for scanning cost, the point right here is take a look at the number of lead pages. Okay? So just down. Other than the cost, just like the other structure, okay, we have 0.15 BD. Okay, so that's the number of lead pages for scanning, right? And you also need DR. I won't go into much why these are adding this way, but the point is right here actually. Why does uncluster suddenly need to consider R? R is the number of records per page, right? So you can think of the number of records right here. I should have done it this way. For example, this is one page. One page. This is one page, and this is one page. The reason for unclustered structure suddenly considering R but not the other ones is because when you get to the very end, even though from data entry you found the corresponding data records, it doesn't mean the data records near the one you found will have a data entry value close to the one that traced back, right? Because it's unclustered now. So it's kind of just crisscrossing. So that's why scanning through all of the data records per page now matters. Okay? So that's why here we consider R. So yeah, I won't really put in too much emphasis on the scanning for uncluster, but this is the cost of it. Okay, so uncluster, when scanning, this part adds a lot of the cost. I think more importantly will be the search. So let's take a look at the search. So you can see, now we talk about, this is the number of data pages in there, right? So what should be the search for it, the search cost, if you compare to cluster? It's actually really similar, right? Because you just need to trace through the tree first. What do you think? Okay, so the cost will be and this is where we will stop if it's just cluster. But here we take an extra D cost. Why is that? Anyone? Now, if you recall earlier the difference, major difference between cluster and uncluster, then why do we need a D? This is searching. Because you actually have to read the data page itself to check whether that's the one you want, because now it's unclustered, right? So the data records are not ensure to being the one you want. Okay, so you actually have to read it this way. Okay. So this is the case where we only have one record that match. So you will see more of an emphasis on this D when you take a look at matching more than one record. Okay. So again, you think of it, we traverse all the way to the data entry we want, and if it matches more than one data record, unlike last time, maybe in cluster 1, the entry, if it matches more than one data record, then they will reside very closely, right? But now it's unclustered, so you can't make sure it's always clustered in close location. So for your data entry, you might need to keep accessing multiple times. So if you have multiple data records that match, then the cost this time will be like this. So you still have the D, but this time you times it with the number of qualifying data records. Okay? Because now it's unclustered, so it will be necessary for you to access this multiple times. So you might think, okay, now it doesn't look that useful at all. We have uncluster, but it's adding all the overheads. Then why do we even bother to have it? So can anyone remember what will be the cost for searching in sorted file if the assumption is binary search? Anyone remembers? So that in sorted file, if we have these many data pages, we have D data pages, what is the cost for searching in sorted file if the assumption is binary search? How does binary search work? Every time you cut things in half and you decide which half to go, you keep cutting in half, cutting in half. So what's the cost? The cost for searching in sorted file is log 2b, right? So if you compare to uncluster, it's log 2b times d, right? So if you compare to uncluster, do you think it's already an improvement? If we ignore this, do you think that's already an improvement over log 2d? First of all, judging from this part, the 0.15b is already making sure it's already smaller than b, right? Smaller than 1b. And also the f right here, as the f goes up, so as the number of children goes up, the value of the whole thing goes down, right? So this one, if you design it in a way that you have the f in the good number, we won't talk about how to optimize it, but if the f is in a good number, it's potentially, possible that it can beat sorted file, because sorted file, we just do binary search, right? Because here it's short, the base is 2 short. So here, you can change it. But again, if your structure is just 2 children per node, then it's the same. Okay? Okay. How about range search? Range select. I think that's the next slide, right? What do you think the cost for range select will be in uncluster? Do you think it will be the same as the one matching for multiple records or different? So again, when we go back to uncluster, do you think it will help in any way of range select if the pointers are in a crisscross way? Because it's uncluster, so now the order is not being put into consideration, right? So if you have a range of values you want to retrieve, let's say like last time we talked about, maybe you want to find the employees with salary between 3,000 to 5,000, you actually have to go through every single value, right? Like right here, you have to go through every single record. So the range select in unclustered is actually exact same as when it matches multiple records. Okay, so the cost for range select is the same as this. So it's the first searching cost plus number of clarifying data records times 2. It's the same. Okay, finally for insertion and deletion, what do you guys think? Start from insertion. What do you think is the cost for insertion plus the index? Again, the steps for inserting, you have to find the right spot first, and then just do a right. Okay? So that's basically searching plus rec. So what's the search in the cluster? Just here. So we say we want to first do the search. The search itself already takes up this. And then we do the write. Writing is 1 IO. So you plus an IO. Okay, so if you want to make it more concise, then that's just basically plus. Okay, where does these two D come from? 1D comes from the search, 1D comes from writing. Okay. How about delete? Like in cluster, insertion and delete is the same. So do you think on cluster will be the same? Yeah, you need to search through the tree first, find the spot you want to delete, and you just take 1 IO to delete it. So again, for deletion, it's also the log base f 0.15p plus 2. Okay. So just remember, y2d, one of the d is from this plus this, that's the search cost. And here is an IO cost for writing. And here is an IO cost for reading. So you can rewrite again. Okay, so that's all for the cost analysis. So if I ask in an exam, I won't be really annoying asking you to like memorize all of them, but I might ask you, so the answer is this, why? Okay, so you just need to tell me why the cost is like that. Give me explanation, then that will be more than enough. Okay? So we finished the cost analysis, and what's left for chapter 8? Not sure whether we can enter chapter 12 today, but for chapter 8, what is left is to just basically discuss a little bit about selecting the indexes. Okay? So far we are just assuming we have a structure and then we do the cost analysis. But what kind of values are you based on for doing the indexing? For example, in the employee data, we have maybe the age, the salary, the department it's working in, all sorts of data. Then what is the one that you're based on to do these kind of structure? Okay. So now we'll talk about, in different scenarios, what is more suitable. Oh, remind me, there will be a quiz before the lecture ends. Maybe you need 3 minutes more. So let's talk about index selection. So in different times, different applications, there will be different suitable index, okay, based on what kind of attribute you choose for indexing. So here we say, what we want to consider is to consider the most important queries in turn. So in different kind of application, a lot of times what you query the most will be different, right? For online shop, what you query the most is different. Maybe for booking flights, then the application, the most important queries will be different. Okay? So we also want to consider the best plan using the current indexes and see if a better plan is possible with an additional index. So sometimes you might want to index based on more than one attribute or more than one field in your database. So the attribute, when we think about it in SQL queries, in which clause will be a good indication of what you want to choose as index? What do you think? So for choosing index, that's kind of like the order of the values matter, so that's why we structure it, right? So you would do a lot of comparisons against the order. So which clause inside the fields inside which clause in SQL command do you think will help us to give us an idea of what attributes we should choose for index? In which clause inside the SQL command it's indicating here is where we will do comparison because it's criteria.
Where?
Yeah, in the where clause. Okay, so attributes in the where clause are good index candidates. So here we're saying some kind of examples. For example, if in your where clause you're always having just equality check, okay? Then we say exact match condition, we will suggest you can do hash index, right? Because we talked about very early on, for hashing, the cost is so low, right? You just need to compute the hash function and see which bucket to go. That's it. Okay, so exact match, if you do a lot of exact match in your application, in the where clause, then we are saying hash index will be great. However, if today you are having lots of range query, for example, in your where clause, you're always saying salary between 3,000 and 5,000, just keep using this example. If it's within the range, if the range query is used a lot, then instead of using hash index, we say tree index might be better, just like the cluster tree we were using before. Okay? Why not hashing? Because hashing function a lot of times are not guaranteeing the relativeness between the values, right? You hash it and then it completely changed the bucket. If you remember the very basic hash example we work on, from 1 to 10, they will all be assigned into different buckets. So if you use hash, then if you're doing a range query, then you actually have to access so many different buckets. So often, then accessing each bucket is an IO, an IO, an IO. So that will be expensive. So range query, what we suggest will be tree index. Okay? So here we also say clustering is especially useful for range queries, like we said before. Okay? And also, like we just said earlier, a lot of time it's not just based on one attribute that's being used the most. So it's possible that we will also have multi-attribute search key. Okay? So then you might want to build your index based on more than just one attribute. And also, the order of attribute is important, which I'll show you later. So what you want to index based on, maybe you want to base on some attribute A first and attribute B later. Okay? So I'll show you why it matters later. And also here I say, such indexes can sometimes enable index-only query processing. So what do we mean by index-only query? Here, I'll just quickly show you an example. I'm not sure whether I have it. Okay, for example, we have select okay, if we want to select okay, so let's say from the employees table we want to find those with age equal to 20. And what we want to select is just basically we want to count such employees. Okay? So if we do this, it's saying from the employees table we want to find how many employees are age 20. Okay? If today our index is based on age already. Okay, let's say the way we store the data is based on the employee's age. Okay, maybe we sort it in a tree. Okay, so then the data entry is all based on the age. Maybe the root is 18, so when we want to find 20, we go right. Okay, like so. Then we say this is an index-only query. Why is that? Because you only need to count how many index are like that. How many data entry are we saying? So you don't actually have to go to the record itself to see other attributes. Put it that way, right? You don't have to know other attributes. You only need to know the attribute that is used as the index to answer this question, right? So this is what we call the index only. But today, if you are saying, I want to count something else, maybe group by the departments working on. And we say, okay, today not only we want to use this, but group by the department ID. Then this will need to access the attribute other than the one is used for index. So then now, this one is not index only. Okay? But taking this out is index only. Okay? That's what we mean by index only query. So sometimes index only query, as you can see, will help the efficiency a lot because you don't have to access other attributes. So sometimes if you have queries that you think potentially can design as index only, then you might want to find a way to find the attributes to use as index. That will make as many index only queries as possible. Okay? So let's take a look at this example. Example 1. Okay, let's take a look at this query. And I think down there I say, how selective is the condition if everybody is older than 10 years old? So change that into within age 20 to 30. Okay? Because I think what I asked didn't really make sense. Okay, so consider this query right here. Here we say a B plus tree index on the age can be used to get qualifying couples, right? Because here all it cares about is the age. Okay, we are doing comparison on age. So if your indexing is based on age, then that'll be better, right? And also if it's even cluster, because here is a range. So that's the most suitable right here. Okay, so right here, I asked, is the index cluster? I should ask, should the index be clustered? It's yes. Okay, that's it. So we'll see a bit more of these kind of examples. I think for homework 6, I already posted it. It's super simple, as I said on Monday, so it's due next Friday, right? It's super simple. I just give you simple curves, and you just tell me, other than you have to draw an execution plan, which we will talk about next time. You just tell me, okay, what kind of index should we use that will help the most? Okay, so like here we say, if we use a cluster one on H, that's the best for now. Okay, so for that homework, that's all you need. Okay, so like before, we consider a bit more. Now we also consider group by. So in this example, really similar to the one we actually just drew on the board. So now, if we want to find the number of employees that are older than 10 years old and group by the department number. It doesn't really make sense because if you work, you should be older than 10 years old. But anyway, so that's the example right here. If we consider group by, what do you think, what kind of index will be the best? Do you think now we should still base on age? So here we say, if already many tuples have age greater than 10, all right? Then today, indexing on age doesn't help that much anymore, right? But what will help is if we index based on the department number in a cluster way. So you can think of the tree as this. So if you think of the tree as this, and we index them based on the department number, then at the very end, all these pages, if these are data entries, you can think of them when they're assigning to the actual records. It's not exactly like that, but it's almost like each page is a department, right? Because that's how we design it. Then, when doing the counting, it will take less I/O because if you do the age, then every time you still have to search for, okay, now we are considering department 1, and we go to this page and that page and that page. And that's way more I/O than necessary if compared to that design. Okay? So here we say, choosing a cluster tree index based on the department number might be better. Okay, so far we are talking about okay, this one is easy too. How about this example? If we select the department number from employees where the employee's hobby is collecting stamps, then which index do you think we should base on? Just basically based on the hobby, right? Because that's what we care. That's all. Or another one, because now we are doing equality search. So maybe hashing, right? But here, because, let me see. Yeah, hashing will help as well. But here you can also cluster it based on the one that you compare the most. Okay, let me see. All right, I just want to talk about one last thing. So here, other than only comparing one attribute, a lot of times we also care about more than just one attribute. So we say this is a composite search keys. Okay, so right here you can see maybe we have query that we want to find age equals to 20 and then salary is 75. Or you have a range query, but it also involves more than just one attribute. So then this means for the indexing itself, you will want to take more than one attribute for indexing. Okay, I'll show you an example right here. So for example, in the middle, this is the data we are using, okay, we have the name, age, and salary. So in one system, you can index them in so many different ways. For example, the first one, you just index them based on age, okay? So each pointer points to the record that has that age. So you just say, okay, sort by age, that's it. Or here, we can sort by salary. So these are all simple. But what's a bit tricky is here, is when you have composite keys. So if we say we want to index based on both age and salary, then we have these two versions. This one is on age first, then salary. So you can see we have the age sorted first, and then salary follows along. And here, on the other hand, is salary first, and age follow along. Okay, so next time we'll see when should we choose which order. So it actually matters. Okay, it changes the efficiency. And one question before we finish is, what kind of alternative is this, if you recall? Number 2. Why is that? Because we have one each instead of, say, for example, right there, instead of having age of 12 following salary 10 and 20 in the list, right? So we actually have a pair each, pair each. So this is alternative 2. All right, so now take out a piece of paper. You don't have to write this down. So if we say we have 2 queries right here, this one, left one is A, right one is B. And it's indexed based on the salary. Which one is index-only query? That's it. We have these 2 queries, left one and right one, both from the same database. And now, today, the index we use is index based on the salary. So A and B, which one is index-only query? Okay? That's it. If you're done, you can turn it in.